Hello everyone, my name is Nikola Marincic. Welcome to another class, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are currently in week 6, so let's first recapitulate what we did in the previous class. So last time we introduced a cost function called mean squared error, which is a very simple function. To calculate the cost for a single data point, you need to subtract the output of the network from the label and then square the difference. So we computed cost for several data points, and then we showed that as the loss or cost is gradually decreasing, our prediction is improving progressively at the same time. We also computed that the derivative of the mean squared error is -2 times label minus output, which is the same as 2 times output minus label. We visualized our cost function, and it looks like we added an additional layer to our network. Again, the derivative of the cost in terms of the output is equal to -2 times label minus output. In the first example that we did, we tried to reduce the cost for a single data point, and we showed that mean squared error is indeed an excellent function to achieve this, because for a single data point, we can get as close to our label or to our target as we wish. Our optimization looked very promising, so we entertained the idea of pushing as many data points as close as possible towards their targets. To achieve that, we would need to select a data point and plug it into the network. The network outputs a value that you can see on the bottom graph. And depending on the label, there will be a certain distance between the output and our label, which is in this case +1. So our mean squared error squared this distance, and in the backward pass, we try to minimize it. This, in effect, decreases the gap between the output and the label. If we now take the second data point, this will give us another output that we can plot, but now we need to measure the distance between this output and its corresponding label, which is in this case -1. So again, after squaring this distance, we are effectively trying to minimize it. So since mean squared error is just so good at minimizing the distance between the neuron's output and the label, our idea was to achieve this for all the data points. This is how we wanted our prediction to look like. However, when we implemented this in code, no matter how many iterations we run, some data points simply failed to get closer to their label. Some data points did quite well, but some did not do well at all. So this is an illustration of what we effectively ended up with. So I explained to you why this should not be surprising. Forcing a point to get very close to its target is practically the same as equating these two values. So if we do this for all the data points, then we are effectively turning our network into a system of equations. So using only 3 variables, in our case 2 weights and 1 bias, to satisfy this equality for 6 data points, well, this is practically the same as trying to solve a system of 6 equations which has 3 unknowns. And since this system is overdetermined, it will also most likely be inconsistent, meaning that some solutions might work, but some answers will not be correct no matter what you do. However, when we utilize our old optimization strategy, we were able to classify points by using this very same neuron. And the reason being is that this strategy had a much wider range of correct solutions. So as long as the output was higher than 1, we had the correct classification, and as long as it was smaller than -1, we had correct classification. So what we did then is we implemented an optimization strategy which would take the best parts from both of these examples. So this strategy should allow us to measure the distance between the output and its target, but also it should facilitate a spectrum of correct outputs. To do that, we added the Sigmoid activation to our neuron. And Sigmoid, as you know, takes any input, in our case this is a weighted sum, and then squishes it into the range between 0 and 1. Since the sigmoid is the last layer of our neuron, this means that the neuron's output will effectively get squished into the same range, which is from 0 to 1. Because of this, the numerical labels that we assigned to our data points before, well, they do not longer work. Actually, +1 still works, but the -1 is now completely outside of our output range, so it is not the best idea to use it as a label. So what we can do instead is we can modify the labels and push them towards the endpoints of our spectrum. Blue labels can keep their label, which is +1, but we need to change the red points to the label 0. As you expect, all the outputs of our neuron are now within the range between 0 and 1. But we no longer expect all the outputs to be exactly 0 and 1. We can now interpret, for example, points distance to 0 as the probability of it matching the label 0. And what does this label mean? Which means red point. And we can also interpret points distance to 1 as the probability of it matching the label 1 and its corresponding meaning, which is this is a blue point. So now if we choose a data point and computed a weighted sum, then this sum gets into the sigmoid and outputs a value. In this case, we get a value which is very close to 1. And because this output is closer to 1, we can now say that it has a higher probability of being blue than being red. And we can also measure this. So if we take another data point, which after the sigmoid gets its value around 0.2, we can see that this point is closer to 0. Therefore, it has higher probability of being a red point, and we can also measure this. Also, an interesting location on this graph is the value 0.5. So if a point is around 0.5, it is less likely to be distinguishable as anything at all. So the value 0.5 in this case serves as a boundary between our two classes. So on the left side we have red points, and on the right side we have blue points. But the closer the point is to the left, the higher the probability that this is a red point. And the closer the point is to the right, the higher probability that this is a blue point. Well, we implemented this strategy in code, and we showed that we could use mean squared error to achieve 100% correct classification for 6 or even more data points by using only a single artificial neuron. But this solution only works if we allow for a spectrum of correct solutions. Now we will do exercise number 8, which is the same as the exercise number 6 that we did before that used the old optimization strategy. So what we will do here is we will modify this example to apply the mean squared cost function correctly. And what we need to do is we need to first change the neuron in the output layer because it didn't have an activation. We will add sigmoid activation to it. And finally, after it, we will plug it into the mean squared error function to compute the cost. The biggest challenge to achieve this is, of course, computing partial derivatives. Well, now that we have some experience in working with derivatives, I will introduce a strategy which will help us to achieve this much faster and much more systematic. So the first step is to recognize that there are some repeating features in this graph. For example, we have weighted sums z3, z1, and z2. And by knowing the partial derivatives of these points, computing partial derivatives in terms of all the weights and biases becomes very straightforward. Let me show you how. As you can see, from these particular points, computational paths towards all the weights and biases look exactly the same. And because of that, if we know how to compute partials for one neuron, we can automatically deduce how we would compute it for all the others. For example, we know that the partial derivative in terms of the first weight will be the value that multiplies this weight. For the first neuron, this value will be x. In the second, it will also be x. And in the third neuron, this value will be equal to n1. And we also know that the partial derivative in terms of the second weight will be the value that it multiplies. So in the first and second neuron, this value will be y, and in the third case, this value will be n2. And we also know that the third path, which goes only through the addition circuit, will have all the partial derivatives equal to 1. So when I remove the actual circuit, and when we are left only with this diagram, it is evident that we have one unit which repeats 3 times, and just by looking at the graph, you can deduce the values of partial derivatives. Yeah? In exactly the same way as we did with weights and biases, we can recognize 3 computational paths starting from the weighted sums, but now leading towards the outputs of the previous layer. And since these paths have exactly the same structure, we can expect that finding the partial derivatives will be again analogous for all the 3 weighted sums. So partial derivatives of the weighted sums in terms of the first input will be equal to the value that multiplies it. In the first neuron, this value is a1, in the second neuron it is a2, and in the third neuron it is a3. And for the second input, partial derivatives will be the values multiplying this input. These are now B1, B2, and B3. Now that we can compute partial derivatives in terms of all the weights and biases, and also outputs from the previous layer, we need to compute partial derivatives of the output in terms of these weighted sums. So we need to calculate the partial derivative of the cost in terms of Z3, partial derivative of Z3 in terms of Z1, and partial derivative of Z3 in terms of Z2. So if we know these partials, we can use the chain rule to compute the partial derivatives of the total cost in terms of Z1 and Z2. So as you can see, delta C over delta Z1 will be equal to delta C over delta Z3 times delta Z3 over delta Z1. And in this case, delta C over delta Z3 times delta Z3 over delta Z2. Now let's compute these three partials. So what would be the partial derivative of the total cost in terms of Z3? Well, we can apply chain rule here. So it's just going to be equal to delta C over delta S times delta S over delta Z3. And last time, we have already computed that the delta C over delta S equals -2 times label minus S, and the partial derivative of the output S in terms of the weighted sum, this is just equal to S times 1 minus S, so the output of the sigmoid function. Then, what would be the partial derivative of Z3 in terms of Z1? Again, we apply the chain rule and obtain that this is equal to delta Z3 over delta N1 times delta N1 in terms of Z1. Delta Z3 over delta N1 equals A3, and delta N1 over delta Z1, well, this is just going to be the output of the sigmoid function times 1 minus the output of sigmoid function, which means N1 times 1 minus N1. Finally, what would be the partial derivative of Z3 in terms of Z2? Well, it equals delta Z3 over delta N2 times delta N2 over delta Z2. The first term is equal to B3, and the second term equals, just like before, N2 times 1 minus N2. Now we know all the necessary values to implement our example, so let's do that. We are now in the exercise number 8, which is binary classification with 3 artificial neurons and a cost function. So let's first run the code that we are already provided with. So let's run this. Let's initialize the data and labels. Let's plot it to see what it is. Well, this data and labels, we already worked with this already. It's nothing new. And we have the neural networks architecture. We already did this example, so nothing new here. In the final neuron, we do not have the activation function here, but the output S comes directly after the weighted sum. Here is the code. We have sigmoid function. This function here evaluates the accuracy of prediction before plotting it. Here we plot our classification. So let's run this code. Finally, we have the algorithm here, and we can use it to classify between points. So hopefully this will give us correct classification. As you can see, after 20, 25, 30,000 iterations, we are getting 100% accuracy in predicting the label. If I run this code will confirm that indeed the prediction is correct for all the data points. So what would then be our task here? Where our task is to modify the previous code by adding the sigmoid activation to the output neuron and implementing the mean squared error cost function. All right. So what has changed is, instead of S being this weighted sum, now we have Z3 coming before, which is the weighted sum, and we have S coming afterwards. And then we have cost function, which is label minus output squared. And here we have the partial derivatives in terms of these 3 important points that I mentioned, which are weighted sums Z3, Z1, and Z2. We have already pre-computed these values in our slides, so we will not do it again. Okay, let's do this. So the first thing that we need to do is we need to check our labels. Now we added the sigmoid activation function, which will only output numbers which are in the range between 0 and 1. So we need to change our labels accordingly. So let's do that. Okay, this is a little bit annoying scrolling through all of these plots, so I will remove this. Okay, let's check out our data. So, as we had before, our labels used to be +1 and -1. Well, now we will change negative ones to zeros. So 0, 0, 0, 0, 0, 0. Okay, let's reinitialize them and plot it again. Well, it doesn't really change because we did not change the coordinates. All right, now let's go to our neural network. What do we have here? So here we initialize the weights and biases. Then we do a number of loops here. We randomly choose an index, and then according to that index, we get a randomly initialized data point and its label. We compute N1 and N2, which are the outputs of the neurons in the second layer. Finally, we had S, which used to be A3 times N1 plus B3 times N2 plus C3. Well, the output used to be S, but now this output is actually Z3. Is it? Yeah, Z3 is the same as our S. So let's do that. So this is now equal to Z3. But what is S? Well, S is sigmoid of that value. So S will be equal to sigmoid of Z3. Now this will be the final activation. I will copy that. Now here we computed partial derivatives, yeah, and we had this function sine, which we use to either minimize or maximize our values, depending on the relation between the label and the output. Well, now we do not use this anymore, so I will erase all of this code. All right, now we have backward pass. So what do we need to compute first? Well, we need to compute total cost in terms of 3 weighted sums, Z3, Z1, and Z2. So I will call this, because I cannot write delta C over delta Z3, I will just call it dZ3. This will mean the partial derivative of the total cost in terms of Z3, so I'll call it dZ3. And this will be equal to -2 times label minus the output, times output times 1 minus output. So let's write that. dZ3 is just going to be equal to -2 times label minus output times output times 1 minus output. Okay, now let's compute also dZ1, which is going to be for the first neuron, and dZ2. What is dZ1 going to be? Well, dZ1 is going to be A3 times N1 times 1 minus N1. Okay. A3 times N1 times 1 minus N1. In the same way, dZ2 will be equal to B3 times N2 times 1 minus N2. This will be the partial derivatives of Z3 in terms of Z2, and this one will be partial derivative of Z3 in terms of Z1. So let's write dZ2 equals B3 times N2 times 1 minus N2 this time. All right. But this here is the partial derivative of dZ3 in terms of dZ1. We want the partial derivative of the total cost in terms of Z1, so we need to use chain rule. We just need the partial derivative of the total cost in terms of Z3, which is dZ3, times dZ3 over dZ1. So which means that I can just say that this is equal to dZ3 times all of this. So I'm just applying the chain rule here. In the same way, this value here represents the partial derivative of Z3 in terms of Z2. And we want partial derivative of the total cost in terms of Z2. To do that, we just need to multiply this by dZ3. And we get it. So what I promise you so far is that if we know these three partial derivatives, it will be incredibly easy to compute partial derivatives in terms of weights and biases. So let's see if that's true. Well, if we have dZ3 then A3, B3, and C3 should be just N1 times Z3, N2 times Z3, and 1 times Z3. So let's write that down. dA3, dB3, and dC3 are just going to be equal to N1 times dZ3 and 2 times dZ3 and dZ3. All right, so we have the last neuron fixed. Now let's do the neuron N1. Here we have the A1, the B1, and the C1. And what are they equal to? Well, the A1 is just going to be X times dZ1, dB2 is just going to be Y times dZ1, and dC1 is just going to be 1 times dZ1 or dZ1. So X times dZ1, Y times dZ1, and dZ1. In the same way, we need partial derivatives in terms of the weights and biases in the neuron N2. These are A2, B2, and C2. dA2 will just be equal to X times dZ2. dB2 is just going to be equal to Y times dZ2. And dC2 is just going to be equal to dZ2. So again, the A2, the B2, and the C2 are going to be equal to X times dZ2, Y times dZ2, and dZ2. Okay, this should work. And now we do the parameter update. Let's see what we have here. Well, we had here our previous optimization function, which included this sign variable, which was either +1 or -1 in terms, depending on whether we wanted to minimize or maximize. So let's change that. We do not need that anymore. So now we want to minimize the cost. To minimize the cost, we need to subtract the derivative times the step size from the old value. Well, here we are not really subtracting, we are actually adding. So we are actually here increasing the cost. So to decrease the cost, to minimize the function, we will use negative sign. So A1, B1, C1, A2, B2, C2, A3, B3, C3. Now we are minimizing the function. We are subtracting the A1 from A1 and updating it back to A1. Of course, this is times the step size. Then we get these parameters and then we plug them into these two functions. One is evaluate accuracy neural and one is plot neural simple. So we need to check these functions to see if we need to change something there, so to have our algorithm run correctly. The first function is evaluate accuracy neural, which just tells you how many correct predictions you have in each step that you do this function. So what do we have here? We have the output, final output, which was A3 times sigmoid of A1 times X, whatever. This used to be our old output, S, and now we have a sigmoid function coming after it. So we need to add sigmoid to this function. Then we had this line of code here, which says predicted label used to be 1 if the output was greater than 1. Otherwise, predicted label used to be -1 if output was less than -1. Otherwise, it used to be 0. So this is our previous optimization strategy. Well, now our optimization strategy is to use the range between 0 and 1. So if an output is greater than 0.5, then this will be label 1. And if the output is less than 0.5, the label will be 0. So let's do that. So predicted label is equal to 1 if output is greater or equal to 0.5. Otherwise, our output will simply be 0. So I can erase all of this and say else 0. Well, the rest of the code should not actually change. And now let's tackle this function, plot neural simple. Well, this output has most of the same elements as the one before. So we have the output, which used to be our old output without the activation function. We need to add the activation function on top of this calculation. So this calculation here is just the same as this calculation here, yeah? It's just made in one line of code instead of having 4 lines of code, because here we do not need these intermediate values, so we can just do that. So I just need to add a sigmoid for this thing here. And again, predicted label used to be 1 if output was greater than 1, used to be -1 if the output was less than -1, otherwise it used to be 0. Again, we need to say we will mark our images with one color if the output is greater or equal to 0.5, then we will mark them with value 1. Otherwise, we can say that they're equal to 0. Let's run this code. Let's run this code here as well, and now let's see if this will actually run. Let's see if I made some mistakes. Well, something is going on. But it looks like our network is moving very, very closely, so not much is happening here. Yeah, you see the changes are very small. Why? Well, there is multiple reasons why this can be happening, and the most important reason is step size. Now we have completely changed our optimization strategy, so we cannot expect the same step size to do the job. We need to experiment with the step size. Actually, we need to experiment with our meta parameters, which are the number of iterations, and the step size, and also this value here is a meta parameter, which just says how often do you plot these images here. So each 2,500 iterations. Okay, let's change this. Let's first make less iterations. Let's make 1,001 iterations and check it each 250. And let's make the step size 10 times larger. Well, now something is happening a little bit faster, but still not fast enough. Let's make it again 10 times larger. Let's make the step size equal to 1. Well, you see now it's going very well. We are getting 80% accuracy from only 1,000 iterations. So I'm very confident that this is probably a good value for the step size. Actually, let's make it 2, just to test it. Okay, again, this is very well. Let's just make more iterations. Let's make 2,000 iterations. Oh, very nice. So after 2,000 iterations, we have reached 100% accuracy. Let's just confirm this here. Actually, it is not correct because we did not change this piece of code here. So we need to say output is going to be equal to the sigmoid of this. And then the predicted label is going to be 1 if the output is greater or equal to 0.5, otherwise it should be equal to 0. So now when we run this code, we can see that the prediction is actually correct for all the cases. So we have successfully completed our task number 1. Well, there are some shortcomings to the current optimization strategy that we are using. And what would be these shortcomings? Well, we can definitely see that our optimization improves over time, but we cannot really tell how much it improves. We lack a single objective measure that can tell us that. And the second thing is that this approach is too computationally expensive because we are updating our weights and biases after seeing each data point. So how can we alleviate these shortcomings? So first, let's visualize what we have implemented. We have a data set and we have a neural network. So when we plug our first data point into the appropriate outlets, we get the output. In this case, the output is 0.1369. And this number represents the cost for the first data point. When we plug the second data point in the appropriate outlets, we get the output, which is, for example, 1,2996. And this would be the cost for the second data point. So to compute the total loss or cost would require us to keep track of the outputs for all the data points so that we can eventually sum them. So we need to iterate over all the data points. We have already computed the cost for the first data point and for the second data point, and we should just keep doing this for the third data point, fourth data point, fifth data point, sixth, seventh, eighth, ninth, and 10th in our case. If we somehow manage to track all of these values, we can now sum them. So in our case, the sum would equal to 8,5095. And what is this value? Well, this value is the total cost for all the data points. So this is the value that we actually want to minimize. If this value is minimal, then we for sure know that our prediction accuracy will be very high. What would then be the strategy in terms of partial derivatives? Well, we can do a very similar thing that we did with the cost. So let's say that our neural network has only seen the first data point and then computed the corresponding partial derivatives. In our case, we have 9 partial derivatives because we have 9 variables. And what we would usually do is, upon processing the next data point, we would overwrite these 9 variables with the current values of partial derivatives. Well, in this case, we need to make sure to somehow still keep the values in all of the previous steps. So then we get to compute the partial derivatives for the second data point while still keeping track of the derivatives for the first data point. Then the third point, fourth point, fifth point, sixth point, seventh point, 8th point, 9th point, and the 10th point. So if we found a way to keep track of these values, we can now sum them for all the data points. So instead of having 9 partial derivative values, we now have 9 sums of partial derivatives. And if we know the sums of partial derivatives for all the data points, we can now divide these sums by the number of data points. And in this way, what we get is we get 9 average partial derivatives for all the data points. Yeah? So now we have the average gradient corresponding to all the data points, and we can use these 9 average values to update our weights and biases. So instead of updating our network after processing each data point and computing partial derivatives, we can now update it after processing multiple data points and then computing this average gradient for these multiple data points. And in this regard, we can distinguish between 3 types of neural network training. So far, we have been practicing online training. So the idea behind it is that we would update weights and biases after processing each data point. So what does that mean? So our network processes a data point, computes the gradient, and then updates the weights and biases. Then it takes another data point, computes the gradient, and then updates weights and biases. And it keeps doing this until eventually it sees all the data points. Once our network processed all the data points once, we can say that our training has completed one epoch. So in one epoch, our neural network has processed all the data points once. Another type of neural network training is called mini-batch training. So what does that mean? Well, that means that we update weights and biases after processing groups of multiple data points and computing the average gradient for these multiple data points. So we have the freedom to choose how large our mini-batch can be. For example, we can have a group of 5 data points and then compute the average gradient for these 5 data points and then update weights and biases. Then what we do is we proceed to another group of 5 points, calculate the average gradient, and then update the weights and biases. After we have seen all the data points, we have completed one epoch of training. Finally, we have batch training, which simply means we should update weights and biases after processing all the data points once. So in our case, we compute the average gradient for 10 data points, because this is how many data points we have, and then we update the weights and biases. Well, in this case, one epoch corresponds to one batch. And this will actually be the training that we will practice today. So let's continue where we left off with our exercise number 8. We finished the task number 1, and now we have the task number 2, which says loop through all the data points once, and for each point print the coordinates and the label. Okay, this looks easy. You can just say for current data point, comma, current label in zip of data and labels. What do I need to print? I need to print the coordinates and the label. So instead of current data point, I can say x, comma, y. So then I can print x, y, label. current label. Then I want to do this, I get all the points and their corresponding labels. Okay, what is the task number 3? It says now loop through all the data points 3 times. So in each iteration, print its index, so the index of the iteration, and for each data point, print the coordinates and the label. So let's first do the loop 3 times. So I can say for I in range 3, print the index. And now I get 0, 1, and 2. I can also say what the index is equal to. So I get index 0, 1, and 2. Well, now within this loop, we can store another loop, which will be this one. So if we place this particular loop within this loop, what will happen is that, because this code here is indented, it will run 3 times. And then this code where we print is indented in terms of this one. So this one will loop as many times as we have our data points, and this one will loop 3 times. So now if I run it, I first print all the points and then the index, but it should be the other way around. So I should take this print statement and put it in the beginning. Now if I run this, I get index 0 and then all the data points, index 1 and then all the data points, and index 2 and then all the data points. So why am I doing this? Because now we want to implement batch training, so we need to know how to separate the loops for our epochs and how to separate the loop for our data points. Now the task number 4 says modify the previous code by cumulatively summing x and y coordinates in each loop. Sum x's in the variable sum x and sum y's in the variable sum y. After each loop, print the sum. So let's see what can we do here. We need to cumulatively sum x and y coordinates in each loop. So the main question here is where in this loop should we store the variables sum x and sum y? Yeah. So what we practically want is we need to initialize sum x and sum y somewhere. So sum x comma sum y, we will start by making them equal to 0. And then in each of these internal loops, we want to collectively sum x into sum x and y's into sum y. So what we need to do is this. We need to say sum x plus equals x, and we need to say sum y plus equals to y. So what happens now? In each loop, sum x and sum y are restarted to be equal to 0, and then in each of these loops, when we loop through all the data points, we add x to sum x and we add y to sum y, but we do not overwrite sum, we just add to it. Yeah? And then it says after each loop, print the sum. Well, after each loop means that we need to print it here. Print sum x is going to be equal to sum x, sum y is going to be equal to sum y. Close the parentheses. Let's run the code. So now I can see that the cumulative sum of x's after seeing all the data points is 15.6 and of the y's is equal to -6. And then because we restarted in each outer loop, it is always the same value. So now I would just want to show you that if I just move where we instantiate sum x and sum y, this will give us completely different values. So if I put this before this for loop and run the code, you will see that sum x is 15.6 and sum y is -6 like before, but now in each loop this value gets, what we add to this value is this previous value, and then again we add this previous value. And if I move this sum x and sum y within the most inner loop, what I would get is the sum x and sum y will just hold the x and y values of the last points it has seen. As you can see, the last point in all of these cases is 4, -1, and label 0. So I introduced this exercise just to prepare you for what is coming now, where we need to implement batch training. And finally, we get to the task number 5, which says modify the classification algorithm by introducing epochs and full batch training, which says updating the weights and biases only after the neural network has seen all the data points once. All right, so let's do that. So the first thing which needs to change is we need to loop through all the data points once. And here, what we are doing, we are actually looping, and the number of times we loop is determined by this parameter here, which is number of loops. And when do we introduce this parameter? Well, we introduce this parameter in the function definition here. So this is the 4th parameter of our function. So if we run this function here, we will see that our current value for this parameter will be 2001, and then we plug this here. This ends up being this value, number of loops, and then this value jumps over here, and we loop through this function 2001 time. So we need to change that. This needs to become the outer loop. Yeah? So this will not be anymore, I will not call it anymore number of loops, I will call it number of epochs. And I will also rename it here, number of epochs. So this will be the external loop, and within this we need to have another loop. Yeah. So how would this new loop look like? Well, we need to loop again, and we need to see all the data points once. So how we do that? Well, we did it before. We said for current data and current label in zip of data and labels, and then we changed current data to x and y, x, y. And I want to keep using the label. I do not want to use this current label, because if I'm using it somewhere here, I do not want to make an error. So I will just call this label. So now in this internal loop, I already have the values x and y and the label for all of my data points, so it will go through all of them. So I do not really need this code anymore. Okay, and now for these points, we need to run the forward pass. We need to compute final activation, and now we need the cost for a single data point. So this cost, we will call it C, is just going to be equal to label minus this output S squared. Well, now what is this value? Well, this is the cost for a single data point. Which point? Well, depends in which loop, internal loop we are. But the main point here is that this code is on the same line as this for loop. So in order to put it within the loop, we need to indent this code. So when we compute the forward pass, I will select this and press tab, and now we will indent this code. So now this would be cost for a single data point. Okay, and then we also compute the backward pass for all of these points. This is already fine, this is working. So we need to indent this code as well. Well, we now need two things that we need to introduce. And the first of these things will be the total cost. So where will we initiate total cost? Well, we want to know the total cost for all of our data points. And we will see all of our data points in a single epoch. This means that for each of these epochs, we need to restart the variable total cost and then update it with the values for cost of single data points. So I will make here a variable total cost, and I will instantiate it to 0. And now, when we loop through the internal points, when we compute the cost for a single data point, I will add this value to the total cost. So total cost, we will add to it this value C. So in this way, total cost will be larger or smaller each iteration. Okay, and in the backward pass, if we use these values D, Z1, D, A1, DB3, DC3, and so long, If we continue using in this way, we will simply overwrite them in each next iteration. So in each of these loops, we will overwrite the old values. So we need to introduce some kind of new values, which will keep track of what the value was before and then just add to it. So how do we do that? Again, we need to compute the average gradient for all the data points, and all the data points we see in a single epoch because we're using batch training. Well, because of that, we need to restart the values of the partial derivatives in each epoch. So we should instantiate these temporal values here. So I will call them A1, A2, A3, B1, B2, B3, and C1, C2, and C3. And their derivatives would just have D in front. But then if you use these variables, they will be exactly the same as the derivatives. So we need to mark these new variables with some name to distinguish them from the variables which will keep partial derivatives for individual data points. So to these values here, we want to actually add partial derivatives for each data point. So how can we do that? Let's call them temp dA1, temp dA2, temp dA3, temp dB2, dB2, temp dB3, temp dC1, temp dC2, and temp dC3. So if we want to reset them in each epoch, we need to make them equal to 0. So we can do it in a very ugly way, which is like this: 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Or we could do it by using the numpy function mp.zeros, and then we say how many of them we need, and we need 9 zeros. So this will create a list of 9 zeros, and to each of these variables, it will set them equal to 0. Okay, now what do we do here? Well, now we compute the backward pass and all the partial derivatives for a single data point. But what we need to do, we need to add these values, dA1, dB1, dC1, dA2, dB2, dC2, dA3, dB3, and dC3 to these values. So how can we do that? We can say temp dA1 plus equals, which means add to it dA1. What this will do, this will add the current value of dA1 to temp dA1. Then in the next iteration, this will be a different point, it will overwrite it, but then whatever it is, we will add it back to temp dA1. And after we compute the gradients for all the data points, this variable will store their sum. So let me do this quickly. A1, A2, A3, B1, B2, B3, C1, C2, C3. And this one has A1, A2, A3, B1, B2, B3, C1, C2, C3. Well, I must apologize for this kind of code because this code is a total catastrophe. But since I do not expect you to know how to program, I need to do it in the simple possible way. Later on in this course, we will find a more efficient way to do this. Well, after we finish looping through all of our data points once, so after this internal loop is finished, we will have the average gradient computed in these variables here. And then what will happen is we will run another epoch. When we run another epoch, all of these values will be reset back to 0. So we need to do something to them before they get reset to 0. So what we need to do then, we need to do the parameter update with them. So now we will not anymore subtract from our values A1 to C3 the partial derivatives for a single data point, but we want to subtract the average partial derivative for all the data points. So the only thing that we need to change is, instead of subtracting dA1 times step size, we need to subtract temp dA1 and also temp dB1, temp dC1, temp dA1, temp dB2, temp dC2, temp dA3, temp dB3, and temp dC3. Okay, and there is one more thing that we need to do, where at this moment these variables, they are just the sum of all the partial derivatives. But if we want the average of all the partial derivatives, we need to divide each of these values with the number of the data points. So let me first instantiate the variable data length, and this will be equal to length of our data. And now what I want to do is, before the parameter update, I want to divide each of these values by the number of data points, which is this data length. So let's do that. We'll just copy this. Put it on this line. Well, I want to do this when we compute the average gradient, yeah? So which is after looping to all of these points. So I do it here. I do not indent it here, yeah? Very important. So instead of adding the value of DA1, I'm just going to divide by the data length, which is this. And now we can do the parameter update. As you can see, this code looks incredibly horrible, and this is really a bad style of programming. But at this moment, we are interested in how the code actually works. We are not trying to optimize it and make it pretty, but we will definitely do it until the end of this course. So this now should actually hopefully work. Let's try to run this code and see if it works. Very good. As you can see, the code runs and it's actually very, very good. Already at 500 iteration, we are getting 100% accuracy. Yeah. So let's see what would be the minimum number of epochs that we need to run to get 100% accuracy in this case. Let's do 100 and plot each 25 times. Okay, this is not enough. Let's do it 500 times and plot it every 100 times. As you can see, already 500 epochs is sufficient to get to 100% accuracy. And if I run this code, you will see that all the predictions are correct. So in this way, what we actually do is we update our network only when we know the average gradient, which is actually in these variables here. So this saves us some time in computation. And we have successfully finished the task number 5. So another thing that we could do in this example is we could address the total cost. So we computed it, but we actually never printed what this value is. So right here in this code, we added the cost for a single example to the variable total cost, but we actually never printed it. So where we could print it is here. So after a certain number of iterations, we could say what would be the total cost. So we could say print total cost is going to be equal to total cost. Well, in this case, we do not even need to run these functions evaluate accuracy neural or plot neural simple in order to see that we are actually getting better. We can just conclude that we are getting better if our total cost is going down sufficiently. So I will just comment out these functions, and now we will just print the total cost, and we will print it every 10 iterations. So let's just run this code. As you can see, total cost starts with a relatively high value, which is 5.5131, and this is the cost for all the data examples. But as you can see, as I run this code, it gets less and less. And now if I run this code here, you can see that I have 100% accuracy, and this is because this total cost became sufficiently small. And if I choose less iterations, for example, only 100, you can see that the cost now only went down to 1,72. Therefore, there are a couple of incorrect classifications. So by knowing total cost, I can more easily determine how many iterations I need to do. So if I do 500, total cost is getting very low, and this almost guarantees me to have 100% correct classification. So now let's do an example where we implement a network with 2 neurons in the input layer, 3 neurons in the hidden layer, and 2 neurons in the output layer. So why would I introduce this particular network? Well, because this network is the simplest case of a network that still has enough complexity that you will encounter in much larger networks. So in much larger network, you will experience exactly the same challenges as you will have in this very small and simple network. And now let's see what these challenges actually are. Well, the first challenge has to do with the branching of the neuron's outputs. What does this branching mean? Well, it means that one neuron, for example N1, outputs a value that becomes the input for the two neurons in the next layer. So as you can see, the value N1 branches. In the same way, the output of the neuron N2 also branches to the next layer. And finally, the output of the neuron N3 branches as well. Another peculiarity of this network is that it has two neurons in the output layer. So when we introduce the cost function, which is mean squared error in our case, we need to implement it to handle two inputs, not only one, like we used to have before. So let us first tackle the loss or cost function for the case of two inputs. Again, for our data, we have 10 data points with labels red and blue. But this time we have two neurons in the output layer. Therefore, we have two outputs, which are O1 and O2. So how can we implement mean squared error in this case, so that it still behaves in a probabilistic manner? Well, what we can demand from the first output is to return the probability that its output is a red point. And we can require from the bottom output to return the probability that the output is a blue point. And then we can simply join these two probability values into a vector, which is an ordered list of values. The first value will address the probability of redness, and the second value will address the probability of blueness. So how should we then represent our labels to correctly compute the cost? Well, we need to ask each data point about its redness magnitude and also about its blueness magnitude. What we will get is a table containing labels expressed as vectors, and each vector will contain two values, the likelihood of being blue and the likelihood of being red. So the red labels will have a vector that has values 1 and 0. And blue labels will have a vector that contains two values, 0 and 1. So they will have flipped values. Yeah? So now let's see how we can compute the cost of this data point. So we have the following output of our data point. The probability of red is 0.87 and the probability of blue is 0.22. So this is the output of our neural network for the data point which has the label 1 and 0. So this should be a red point, yeah? So then to compute the mean squared error, what we should do is we should subtract the corresponding elements, square them, and then add these two squares together. So what we do is we take 0.87 minus 1 squared, then add to it 0.13 minus 0 squared. We get 0.0169 plus 0.0484, and the total cost will then be 0.0653. So this will be the cost for this specific data point. Yeah? And now you can see that when the output of the network is very far from the label, we will have a relatively high cost. In this case, the cost for this data point will be 1.3369. But if the output is actually very close to our label, as it is in this case, then the cost will be a very small number. For example, 0.0002. So in this case, we have a very good prediction. And if we wanted to visualize our network, this is how it looks like. The colorful frame marks the objective or cost or loss function, depending on how you want to call it. So to compute the cost in this case, what we do is we subtract the labor from the output, square it, and then sum the two squares to get this term TC, which stands for total cost. And now let's compute the gradient of this network, as this is the most challenging thing. Again, let's first mark the most important points on this graph. Now we have 5 points. We have P1, P2, and P3. They are in the hidden layer, and we have Z1 and Z2 in the output layer. And we already know how to compute partial derivatives of the total cost in terms of Z1 and Z2. This will be exactly the same as we did in the last example. But now the challenge is to compute the partial derivatives in terms of P1, P2, and P3. And why do I say this is a challenge? Well, let me show you. This is because of this branching that we have introduced. Let's first tackle the partial derivative of the total cost in terms of P1. Here, the output of the neuron containing P1 becomes the input for the two neurons in the next layer. And because of this branching, to compute the partial derivative of the total cost in terms of P1, we need to sum partial derivatives from the two paths that lead to P1. And one will involve Z1 in the first neuron, and the other one will involve Z2 in the second neuron of the output layer. Therefore, to compute the partial derivative, delta Tc over delta Z1, we do the top branch first, which is delta Tc over delta Z1, times delta Z1 over delta P1, and adds to it the bottom branch, which is delta Tc over delta Z2 times delta Z2 over delta P1. To compute the partial derivative of the total cost in terms of the weighted sum P2, we have the same situation. The neuron in which the P2 is located branches into the next layer. And because of this branching, we need to add partial derivatives from the two possible paths that can take us from the total cost Tc to P2. And one route goes through Z1 and the other route goes through Z2. Finally, to compute the partial derivative of the total cost in terms of the weighted sum P3, we also need to take into account the branching. So the output N3 now branches into the next layer. And because of the branching, we need to add partial derivatives from the two possible paths that can take us from Tc towards P3. And one goes over Z1, while the other one goes over Z2. And then we get the formula. So here we have the exercise 9, which is 2 times 3 times 2 neural network. It just means we have 2 neurons in the input layer, 3 neurons in the hidden layer, and 2 neurons in the output layer. So we want to implement this network. And I would really suggest that you try to implement this alone. This would be your homework. If you know how to do this without my help, this means that you successfully mastered the concept that we have learned so far, and then you're ready to go to the next step, which I will tell you later what it will be. So let's first run the code that we have been given. So we initialize data and labels, and then we have the function plot data. We have the same data points as before, so nothing new here. And here we have the illustration of the neural network that we will be using. As you can see, it's architecture. And then we have a couple of tasks. So first one is write a function convert label, which takes as an input label, which converts the textual labels to probabilistic 1, 0 and 0.1. So let's see what our labels looks like. Well, they are actually textual strings that are either red or blue. All right. So let's make this function. So let's type it, def convert label, which takes as an input label. Well, if our input is, for example, string red, so if label equals red, then what should we do? We should return a tuple of numbers in which the first number will represent the probability of the point being red, and the second number probability of it being blue. So for a red point, this number should be 1 and this number should be 0. So we can just return this tuple, which is 1, 0. Otherwise, if the label is equal to blue, we should return the opposite tuple. So return the tuple 0, 1. Because in this tuple, this is the probability of the point being red, which is 0, and the probability of being blue is 1, or 100%. Okay, now it says test this function with some values from labels. So let's test it. Paste, convert label, and I will plug inside what? I will plug red. So if I plug red point, it should give me 1, 0. If I plug blue point, it should give me 0.1. And if I plug the label, for example, labels with the index 0, then this should give me the appropriate tuple for the red point, because the first data point is red. But also, if I take the second point, it will give me the blue point, third point, it will give me again the red point, and so on. So this works. And now it says, write a function forward pass with all of these inputs, super ugly function, very inelegant code, that takes as an input all weights and biases, obviously, and the current data point, x and y, yeah, and returns the function's output as a tuple O1 and O2. So what are O1 and O2? These are these values here, O1 and O2, yeah, before it goes to the cost function. So let's do that. Let's just copy this here. So what do we have to compute? So we have n1, n2, and n3 first. So let's do them. So n1 should be equal to a1 times x plus b1 times y plus c1, and then we have a sigmoid on top of this. Okay, it should be very similar for n2 and n3. So n2 and n3, this should be a2, b2, and c2. And this one should be a3, b3, and c3. So now we have these values here. Now we need to compute O1 and O2. So O1 will be A4 times N1, B4 times N2, C4 times N3 plus D4. So let's write that. O1 will be equal to A4 times N1 plus B4 times N2 plus C4 times N3 plus D4, and let's copy paste it. O2 should be what? A5, B5, C5, and D5. A5, B5, C5, D5. Again, we have a sigmoid activation here, so we need to plug it. Sigmoid of this. And now we need to return the tuple O1, O2. So let's just return it because we have computed it here. So return O1, O2. Okay, we didn't define the function, and this should be it. Our algorithm should actually run. But as I said again, I really encourage you to implement this algorithm on your own first. Train neural network. And run this code. As you can see, after 300 iterations, the total cost went down. The good thing about the total cost is that even if I did not visualize these points, even if I did not do this plot neural simple, nor compute the accuracy, but just print the total cost in each example, by these numbers I can now see that our network is improving. As you can see, as long as these numbers are getting smaller, I know that our prediction is getting more and more correct. So this is the role of the total cost. Finally, if I run this code here, it will tell me, okay, there is only one incorrect example here. So let's just run it once again. I will print this each 100 iterations, make it 500. As you can see, now the total cost is going down dramatically from 5.27 up to 0.15. And now I'm almost guaranteed to have 100% correct prediction. As we have seen in the previous example, the larger our network becomes, the more variables it contains and more branching it involves. And if you try to tackle all these weights and biases individually, as we did so far in our code, the code will become much longer, much uglier, and much less efficient. And you already seen how ugly our code can be as our network increases. So imagine if our network actually has 1000 neurons. We would then have thousands and thousands of variables to keep track of, and it would be practically impossible to compute the gradient in this way. So we really need to abstract from this approach. Instead of dealing with weights and biases individually for a single neuron, we need to utilize data structures that can deal with whole layers of neurons at the same time. And we also need operations that can compute with such large structures containing the whole layers of neurons. And for that, the mathematics that we know so far is simply not sufficient. So this is why in the next class we will be covering linear algebra. Linear algebra will provide us with instruments that can help us to reach another level of abstraction to understand neural networks, but it will also provide us with the very powerful logistics to actually implement these networks in code. So this was all for today. I hope you enjoyed it, and I will see you next time. Goodbye.